Hello everyone, good morning. I'm Christoph from HPE and today from Cisco on behalf of our vendors that were participating here in this test or this demo. We'll present the results and present what the demo is about. So that was actually the most extensive demonstration during the EANTC probability testing event because it involves a lot of different kinds of technologies. So all of our tests were focusing on one technology. So here, as we will see, we have a lot of different complex technologies. So what was the test purpose here? So here, the main objective was, to verify the performance and interoperability of 5G xHaul transport network using various technologies. So in part of the network, we have SRv6 under the transport. In some other parts of the network, we have SR-MPLS under the transport. So SRv6 only was in the front hall, so between the audio components and so on. SR-MPLS more in the mid-hall, back-hall. So which means that we not only show the interoperability of SR-MPLS and SRv6, but we showed as well the interworking gateway function. Yes, so in order to communicate between SR-MPLS domain and SRv6 domain, we need to have some interworking functions. So we show this as well. Compliance to the ORAN Working Group 9 standards. So ORAN Working Group 9 is the transport working group which defines, the requirements for the ORAN transport and so on and so on. We showed as well here the effective handling of the fronthaul mid-hall backward traffic across multi-vendor environment. By effective, I mean we prioritize the fronthaul traffic, which is the most important. So you will see that we have no drops, no delay, and so on the fronthaul traffic, and at the same time on the backward traffic, maybe there's some drops and so on. And the service orchestration, so in the second half of this presentation, today we present more data here, layer 2 and over SRv6 locator, switching between MPLS and SRv6 domain, and as well service account assurance, so TWAMP, we do some TWAMP study. So what are the challenges with 5G fronthaul? So 5G fronthaul is very, very specific, or it puts a lot of requirements, or hand requirements, I would say, maybe not lot of requirements, but hand requirements against the transport network. So what are these requirements? So first of all, it's extremely low latency. So here we're talking about the microseconds, a couple of tens of microseconds. This is what is the expected maximum latency, and not milliseconds like in general internet traffic, we are talking about milliseconds. So here's microseconds, couples of tens like, 40, 50 microseconds, up to 100 microseconds. This is what our government specifies what kind of latency maximum is permitted here in the fronthaul traffic. Then the second, no drops. So even if there's congestion on the link, we should make sure that on the fronthaul traffic, the CC3 traffic, there is no drops. So it should be highly prioritized, no drops, no latency, and so on. And as well during the congestion, the timing synchronization distribution. So PTP as well is not affected during the congestion. So there will be second demonstration today afternoon on the same topology, so the same use case, concentrating on the timing synchronization aspect. Yes, in this demonstration that we are doing, we are not concentrating on the timing synchronization, but on exactly the same topology that we will do some second demonstration today. And then key elements of realization, so we use 75.1, so G82 75.1 telecom profile for timing synchronization. That will be discussed today afternoon on another presentation. But what we will show here today is packet classification based on IPv6 traffic class. So in order to prioritize this EC3 traffic, or Ethernet priority for EC3 traffic, Ethernet priority power points. And as well, TSN, so time sensitive network profile A for fronthaul traffic prioritization. And prioritization of critical packets assimilation that will be after this. So this is the topology that we used in Berlin. Here we have slightly smaller topology, not all the devices that were used in Berlin where I use here actually. And what we have in this topology? First of all, we have some, access network, we have aggregation network, and we have some core part of the network, and then we have different vendors participating in this network. Yes. So you have Arista here on the left side. Let me go back. Sorry. So you have to use that with Arista here. So you have some Arista devices for it. We have some Arista here devices in the network. We have some Ciena devices in the network, as you see. You have in a couple of places Cisco devices in the network. You have as well Ericsson, so here's Ericsson, so 2 devices. HP devices, so we have 3 HP devices in access aggregation before. And we have additional vendors. Next vendor was Nokia, so we have Nokia as well here in the core part of the network. Raisecom, so Raisecom in the aggregation network, and ZTE as well in the access aggregation. So as you see, it's quite complex. A lot of vendors, almost all of the vendors that were participating in the event were here. So I think only 1 or 2 vendors are not presented here. So it's quite complex, across so many vendors to implement this stuff. So here in Paris, there will be a little bit smaller set of these vendors, so Sujay will show later on the orchestration, how it's network is like in parts. Alright, and then, as I mentioned, so we have complex networks on the left side, on the frontal part. We have, so on the left side is here, so on the streets. So we have ISIS level 1 SRv6. So here the underlying transport technology is SRv6 that we are using. Again, a lot of interworking between Interop between different vendors. On the right side, we have ISIS level 2 SR-MPLS. SRv6 is of course IPv6 based. SR-MPLS is IPv4 based. So we have not only different encapsulations like MPLS and SRv6 in different parts of the networks, but we have as well different control planes. So in one part of the network, control plane is based on IPv4, another is based on IPv6. So that answers well the complexity of the overall network. Then we have some, timing synchronization devices. I mentioned the Microchip Grandmaster, but later on afternoon there will be a session dedicated for the timing synchronization, so we're not covering here in more details. And then we have as well, surrounding this network, we have some helper functions, let's say in this way. So we have of course Keysight that is providing, a generation of the background traffic and some kind of emulations. So first, most importantly, that the Keysight we have on two sides of this network, which generates some huge amount of the traffic for the background in order to congest the network, yes, so that you see the congestion in the network. And then, in addition to this background traffic generation, Keysight as well is doing emulation of the radio units and distributed units. So you open radio unit, open distributed unit. This is emulated by Keysight equipment here. So we have two RDUs connected to the access and to the aggregation. And then the next one is PSA. This is again for the timing synchronization. I will not cover it here. Today afternoon there will be a session covering the timing synchronization data, but first, of course, here Keysight is and the place as well. So that was ISIS configuration, yes? Now from the BGP perspective, ISIS and the transport, yes, MPLS and SRv6. Now from BGP perspective, we have the BGP router vector, which is on the aggregation layer, so that it can, reflect the prefixes from the SR-MPLS, IPv4, to SRv6, IPv6. So the function of this router vector is not only router vector as such, but as well is doing some kind of BGP network layer distributed information conversion between MPLS and SRv6 and vice versa. Yes, because on one side of the network we are speaking MPLS language, on another side of the network we are speaking SRv6 language. So this router vector is not simply reflecting the prefixes from left to right or from right to left, but as well is doing some conversion of the information from MPLS to SRv6 information and from SRv6 to MPLS information. So it's more complex function. Yes, we call it conversion. For ISIS, as I mentioned in the previous slide, there's no leaking of the information. So which means, we have this ISIS SRv6 domain, ISIS MPLS domain, no information is exchanged at the ISIS level. Okay, it's completely locked from left to right and so on. The only information exchanged between the domains is at the BGP level. And doing this exchange of the BGP information, we are doing for the conversion as well of the BGP advertisement. And now the topology services. So we are doing, let me start here. So we have a couple of layer 3PS So there we mentioned the later on the orchestration and so on, but here's some management VPN, which is present essentially on all the devices in the network. So there's some management VPN to manage the devices in the network. So this one kind of service that we are placing here in this network. And here again, in order to communicate between the MPLS-based management VRF and SRv6-based management VRF, on the data plane, when you start the traffic from left to right and from right to left, on the MPLS domain, this traffic is MPLS encapsulated. When it reaches again the aggregation layer, this aggregation router, the aggregation router needs to convert the data plane, the packet itself, from MPLS encapsulation to SRv6 encapsulation. And then vice versa, yes, when I receive packet from the aggregation router receive SRv6 packet, it's encapsulated with SRv6, IPv6 headers, and so on and so on. This aggregation router needs to convert this packet to MPLS, so change encapsulation. So the function of this router in the meter has three functions. This essentially this rot reflector, so you're doing BGP rot reflector. And when doing BGP rot reflector, you're doing control plane convergence or conversion. And then under the data plane level, you're doing the encapsulation change. So you're calling the SRv6, SR-MPLS gateway function for the API. Alright, then the next one what we have is EVT and VLAN. This is the service type that we are using for ECP traffic. So ECP traffic is enhanced or extended, whatever. It's not exactly specified. CP is a common public radio interface. This type of traffic that is in the front door network of the mobile architecture, so between LU and U. This ECP traffic is generated by the Keysight LU and U emulations. And in the transport network, we place this ECP traffic inside of EVT VLAN service, because this is layer 2 traffic, so ECP state traffic. And this traffic is present only in the SRv6 domain, yes, because it's traffic between all the U and the U, so it's not extended to the level 2 domain with MPLS. And then the next service what we have is for the background traffic, as mentioned before, so the Keysight is generating some background traffic as well to saturate the links, so to congest the links in the middle somewhere. And for that, we have simple layer 2 VPN, two locations to generate this background traffic. So this is our topology, so to say. And then we start with the traffic. Yes, so we have some ECP streams going from the OLU to OLU. These ECP streams are going across access and aggregation layer in our topology, and they are delivered inside of EVT and VLAN over SRv6. Then we have some anomalous streams called background traffic. They are very thick. So which means the streams here in the access aggregation domains, these things will become congested, yes, because the background traffic is so huge that in addition to this ECP traffic, these things will be congested. And the point of the game here, the point of the testing is to make sure that ECP traffic and EVT traffic is not affected during this projection situation. And for that, what we are doing here is we are applying TSN, so time sensitive networking profile A, to prioritize this ECP traffic, all right, over the background traffic. I think, yeah, that's you.
Yeah, so for the automation piece, right, what we have here is to showcase between where Cosmo can do the automation for a multi-vendor topology on 2 different domains. So what we try to orchestrate is what is the layer 3 VPN service, and then also have the TWAMP groups connected across the endpoints so that we collect the assurance and activity metrics. Now, the first use case is to show that we can orchestrate a layer 3 VPN service across 2 different domains, and then the validation through the traffic. The second is to do the stitching on the gateway, right, which is the HP and the route reflector here in the aggregation, and to do the stitching between them so that you can overlay for the services and then have the end-to-end connectivity between those 2 domains in the network. So in this case, what we are orchestrating is doing the stitching and then the layer 3 VPN service. And then for the validation, we are also using the QoS settings that is set across the network. These are different low priority and high priority traffic intent. So as part of the EANTC test procedure, I mean, these are the list of orchestration steps that we needed to set up, prepare, and visualize. But I'll show this in the demo for the use case. All right, so this is right now the live topology that we were able to collect across all the vendor nodes that we are visualizing here. So between the access nodes, between Cisco, Ciena, and HPE, and then on the aggregation, here we have most of the vendor nodes, Ericsson, Raisecom, Ciena, HPE, and on the top. And then on the core side, we have Nokia, HPE, and Cisco. Right, so we've collected this topology details, the traffic visualization of our services, and then I'll try to orchestrate that between them. So right now what we have is we use this orchestration engine to provisioning for various services intent. Here we have a bunch of services that are already being pre-created. But what I'm going to try to do now is to switch on the also because it's a best of both effort to show between both CLI and CNC as we use. So this is on the core side of the routing that we are learning all the routes. But then if I try to make this connection and do a ping here in this case, I would not be able to connect because right now the switching service is not enabled. But although I have a layer 3 VPN service across them, I'm not able to connect. And the idea is to also measure this assurance through PCA, which is, we have the TWAMP probes, right? We have the TWAMP probes running between those two endpoints. Now, where I'm trying to manage is between Cisco 235, that is on the core, to the access, which is HP 289 and Cisco 250. And this is kind of, we're collecting this historically data right now to see that because there's a loss, it's still red. So it'll collect you on the assurance. It'll tell you that the service is not able to switch. So the service assurance parameters, it'll tell you what is the packet loss that is implementing. And then the TWAMP level of information available for those endpoints. Now I'll go back to the screen here to say that if I put back the configuration on the HP here to apply the route policy, so which is for my case, I'm going to do the set to the orchestration and do a commit. So immediately I should now start looking at this is when I start to do a ping, in this case, it'll start connecting, right? So I'm able to form the connection and then the overlay test between them. And then likewise on the L3 VPN service assurance, I mean, it will take a few seconds, but let me see if I can, show this for the past 8 hours where we've been running this test. Is eventually it will gradually move from red to orange to green. Right, so this is where you will start collecting this to show on the assurance feeds that when the service is aggregated and it's able to form the assurance between those two endpoints, and then we can orchestrate them across the services and across various nodes.
Yeah, let me show a couple of pieces in the live demo. Yeah, I wanted to show as well, because now the service is enabled. Before the service was not enabled because the switching was enabled.
Yes.
Yes, and now the service is enabled. That's the reason I can show as well a couple of things here. What's happening here. This is the aggregation node that was sent out before. And let me show you here. So we have a couple of agencies, network was bigger. One of the agencies here is on this interface during the access router, in the direction of the access router. Yes, this HPE 298. This is the access router, we are the aggregation router. So this is the link that is congested at the moment. And just one command then. Okay, one command because we need to finish. And just one command. So here's the QES, what I mentioned before. You see, there's a couple of things in the forwarding class best effort being dropped, and there's nothing dropped in the forwarding class network controller when we put the front contract. So thank you very much for your attention. If you have any questions, of course, we are available.